All right, good morning. So today I'm going to talk about gauge invariance. In quantum mechanics. So surprisingly, a good reference for this topic is Kittel. And it is in, at least what I have today is based on Kittel's appendix G. So first, let's start with fields and potentials in electromagnetism. Fields and potentials. So electric field is written in terms of a scalar potential, and if we also have like a vector potential like this, and magnetic field is a little bit simpler. It's like curl A. Here we call phi the scalar potential, A the vector potential. And by gauge invariance, what I mean is take A and change it to A plus a gradient of a function, and take phi and change it to phi minus time derivative of the same function. And here I don't write the arguments, but chi is a function of position and time, possibly. Then it is very easy to see that, okay, the argument is A and phi are not physical, E and B are physical, and these unphysical objects which are potentials should not influence. How you choose these potentials should not influence what you observe in physics. And we can see that is actually indeed the case. So let me substitute here this thing. This is the new gradient. And for A, I'm going to substitute this. And one can see this is the gradient of time derivative. And there's like minus, minus, plus, minus. Time derivative, okay, there is, I think, 1 over c here. So there is 1 over c here. So minus, minus is plus. This term is going to cancel this term. And if I call this one the prime after change of gauge, it's going to be equal to E. And similarly, if I have B prime is equal to curl of A, which is going to be curl of this thing. But we know curl of gradient is 0, so this is going to be curl of A, which is the, so this is E, this is B. So that's what we call gauge invariance. Now we have to consider a particle in an electromagnetic field, and for that I'm going to start with classical Lagrangian. So classical Lagrangian is equal to L 1/2 m v squared minus q phi plus q over c v cross v dot a. Here v is equal to dr dt. And the question is why is the Lagrangian like this? Do you know why the Lagrangian has this form? Any
it's the kth term plus the potential.
Yes.
Minus the potential term.
But in the vector potential, right? Well, is there any reason for us to take the Lagrangian? What's the argument for us to take Lagrangian like this? I think as far as I know, yeah. Exactly. So this is going to give us the equation of motion, and I want to just quickly derive this. Let's obtain the equation of motion and check. So I need to calculate. Okay, equation of motion is obtained from Lagrangian, and it is given like d dt del Lagrangian del x dot minus del Lagrangian del x is equal to 0, and same for y and same for z. So let's only calculate the x component, and y and z are going to follow. First, del Lagrangian del x is equal to, so in the first term there is no x, in the second term minus q del phi del x, and here there is no x, but inside a there is, okay, let me write this, plus q over c. So this is x dot ax plus y and z, so this is y dot a y and z dot a z, and when I take the derivative, it's not x dot is independent of x, so it's only going to act on the second part. Okay. So this is del a del x, and the last one is del a del x. Similarly, I have to calculate del Lagrangian del x dot. So there is x dot here, so this is like x dot squared plus y dot squared plus z dot squared, and if I take the derivative, I'm going to have m x dot. There is no x dot in the second term, and the last term is going to have plus q over c x dot times ax. Now I need to calculate d dt del Lagrangian del x dot. The first term is simple, m x double dot plus q. I think so this is missing. I took the derivative, so it's only mx dot plus q over c. So this is q over c. So ax depends on x, y, and z. Same for az, same for ay, and same for az. So then I need to take the partial derivative. So this is dAx dt, but this one is going to be del ax del x x dot plus del ax del y y dot plus del ax del z z dot, and possibly there's also like explicit time dependence. This is going to be del ax divided by del t. Now I put all of these in the equation of motion. So from here I have m x double dot plus, let me write this one, is equal to this one, and let me open up some space. Here I want to take this q over c del a del t to here, and I have minus q, so let me put minus here. This is minus del L del x minus 1 over c del a x del t, and I am done with this term. and I look at this is del A del X, del AX del X, del AX del X, this is X dot, this is X dot. So this term is going to cancel this term. Exactly.
I didn't understand why did you cancel this partial derivative with respect to time?
Partial derivative like this term. So I didn't cancel it. It was here. I took it on the other side of the equation, and it picked up a minus sign on the other side. So this one and this one they cancel. They are exactly the same. And so these two terms I can carry it on the other side. So like this. So this is minus Q over C times this entire object. And if I rewrite this equation, it is going to be, so this first piece is electric field. So let me write that. M x dot is equal to Q E x plus Q over C. So now I'm going to write y dot terms. So y dot del A y del x. So I've taken care of this term. And there is another y dot with the minus del A x del A y del x del A x. I think that's correct. Yes. Del L A, yes. Del, this is del y. And this is plus again Q over C z dot. So this term del A z del x, and with the minus del A x del z. But if you remember, B is equal to curl A, which is going to be del x del y del z ax ay az. So the first term here can be identified with, like, this is the y component, del this is the z component, del ay minus del ax. Yes, this is b z component. And the last one here, this one, is going to be, I close this row. This is del x az minus del z ax, and this is b z. And I think I picked up a minus sign. Yes, I think this is by. Sorry. This is actually minus by. Minus by, right? Then mx double dot is equal to q ex plus q over c y dot bz minus z dot by. But now I look at this term, and this is like, and I calculate v cross b is equal to x dot y dot z dot bx by bz, and the x component of this is y dot bz minus z dot by. So this piece is I think this is v cross b x component, and at the end equation of motion for x is mx dot is equal to qx plus q over c v cross bx, and same for y and z. So if the Lagrangian reproduced equation of motion, it is like a fair Lagrangian. So that's the argument. So once you write the Lagrangian, the second thing is to derive the Hamiltonian. So because we want to eventually go to quantum mechanics, and quantum mechanics work with Hamiltonians. So let's do derivation of Hamiltonian. And for that, Hamiltonian is H is equal to sum over all I pi xi dot minus Lagrangian, and pi is given by del Lagrangian del xi dot. So let's calculate px. So px is equal to, so the Lagrangian, let's copy here to see. So I'm taking a derivative with respect to x dot. So this is going to be m x dot from the first term. So there is no x dot here, plus q over c. There is x dot a x, y dot a y, z dot a z, but only the first term is x dot dependent. So this is going to be q over c a x. So in all components, this is going to be p is equal to m v plus q over c a. Now I can cross this. Sometimes we call this one, it's a little bit terminology, this one is canonical momentum. So this one we call kinetic momentum, and this one we call field momentum. So this is P is equal to P kinetic plus P field. And there's also the reason, there's also the question that commonly asked, why is this called the field momentum? And to answer that, we can basically consider electromagnetism. In electromagnetism, P field is equal to 1 over 4 pi c, the volume electric field cross B field. So do you know the name of this object, E cross B? This is what we call Poynting vector in electromagnetism, and if you integrate that, that's the momentum of the field. And if we assume here a slow moving charge, V over C, much smaller than 1, and B is background, and E is due to charge Q, which means del square phi is going to be given by minus 4 pi Q del R minus R prime. And if you substitute this, of course B, which is curl A, so this is going to be 1 over 4 pi C dV. E is gradient of phi cross del cross A. And so this is, if you want to sharpen your vector calculus skills, you can spend like a few hours to derive this, but if you do everything right, what you are going to find is like Q over C times A. So it actually makes sense to call this object the field momentum, which comes from Lagrangian without any vector calculus calculation. So this is important. Now let's obtain the Hamiltonian using this. H H is going to be, so I'll just take this, so this is P times x dot plus x goes to y and plus x goes to z components, and we need to subtract minus 1/2 m x dot square y dot square z dot squared. Lagrangian was not to pick the wrong sign, so this is plus q phi minus q over c v dot a, and this term is qa x dot, and same for x and y. So this is color red. This one is going to cancel this one. So this is going to be m x dot square plus m y dot square plus m z dot squared, and subtract minus 1/2 from this. I think I can erase this one now. So this is going to be 1/2 m v squared plus q phi. But from here, from this field momentum, we want to write it in terms of total canonical momentum. So this is the kinetic momentum. So using this, we have V is equal to P minus Q over C. So I'm using this to derive this. Q over C A 1 over M 1 over M. Okay, I'm done with this. Then Hamiltonian ends up being P minus Q over C times A squared divided by 2M plus Q phi. Now we can write down the Schrödinger equation. Schrödinger equation, H psi is equal to E psi. And now there's the question of what does the gauge invariance do to Schrödinger equation, and let's write that and see. So I want to take A to A prime is equal to A plus, and for the moment let's only consider the gauge invariance with vector potential. I think the gauge invariance with scalar potential trivial, and it can be done as an exercise. Let me just consider this minus chi gauge transformation. Then Schrödinger equation, let me copy this. So this thing is Q over C, and this one is going to change. Okay, let me rewrite this. This is 1 over 2M P minus Q over C. Now if this is the new A prime, I want to write everything in terms of A prime. A is equal to A prime plus gradient, and this one is going to be Q over C A prime minus Q over C gradient of chi, like this. I think, yeah, this is, so I think this one is plus. I want to do it like this. This one is minus, then this one is going to be plus. And square of this thing is going to hit on wave function. And let's forget about scalar potential. Like I said, that's trivial, and is going to be equal to E times psi. And the trick here is try an ansatz. Like, let's try this psi to be equal to some e to the I alpha times some psi prime, where alpha is equal to some alpha of r. And I want to consider p acting on e to the I alpha psi. This is going to be e to the I alpha. I think we did this same trick with the Bloch functions, but I think let's quickly do it to see it works the same way. This is minus I h bar, I gradient alpha psi plus e to the I alpha p times psi. And I combine these two, so this is e to the I alpha, this is p plus h bar gradient alpha psi. So the p acts on this e to the I times phi in such a way, this is you jump over e to the I e alpha and you pick up this p plus shift. Then this entire thing, so this, if you do this entire thing, let's do it one time first, e to the I alpha times psi. So this is just a constant, it is going to just jump over the wave function the same way. So this is going to be e to the I alpha. So this is going to be p is going to be p plus h bar gradient alpha minus q over c a prime plus q over c gradient alpha gradient chi times psi. And if I do it twice, so this is the square, it's going to be e to the I alpha, just the same thing, squared. Then the Schrödinger equation becomes, so this thing 1 over 2m. I think I forgot the psi prime here. So this is e to the I alpha psi prime. So this one is prime, prime, prime. I think these are all primes, because I want to write Schrödinger equation in terms of prime coordinates. So this is e to the I alpha prime. And this one is also prime, is equal to e times e to the I alpha psi prime. So these e to the I alphas, they did their job, thank you, and we cancel them. And here we look at this equation. So if we can cancel this term with this term, it is going to be exactly the same Schrödinger equation, but only a's went to a primes and psi went to psi primes. And for that to happen, we need h bar del alpha is equal to minus q over c del chi, or alpha should be equal to minus q over c h bar chi plus a trivial constant, and we don't need to take the trivial constants. In that case, the Schrödinger equation is 1 over 2m p minus q over c a prime psi prime is equal to e psi prime, exactly the same Schrödinger equation, only primed. And psi, okay, a prime is equal to a, was it plus or minus? Plus chi. So this is how a is related to original gauge, and psi prime is equal to e to the minus I alpha times psi, but we found what alpha is. It's going to be I q over h bar c chi times psi. Okay, let me show one more thing about this, and then let's take a break. So now we have the consequence of gauge invariance. Let's look at it in a different way. The consequence of gauge for vector potential. Let's consider free particle, and this one is going to be psi. Let me put 0 without a is going to be r, and for free particle we have e to the I p dot r, right? That's the plane wave. But in the WKB, if you remember, so this e to the I px is going to go to e to the I dx p of x. So that's in the WKB approximation. There's also I over h bar here, so this is I over h bar, and there's I over h bar. But since p goes to p minus q over c times a, this suggests psi with the field in the presence of a field is going to be psi of r is equal to this psi without the field times e to the so I'm going to substitute just this piece here, e to the minus I q over h bar c sum the r prime dot a of r prime going from some r0 to r. So this is the r, this is the r. So then if a particle goes in like a trajectory from like r0 to r, and there is like a background magnetic field parameterized by vector potential phi, that particle is going to just experience a phase shift given by, let me write it like this, phi is equal to q over h bar c from r0 to r. So this is r prime a of r prime, and this additional phase, so this one is called Aharonov-Bohm phase. So let me do one last thing and let's take a break after that. So there's also the question, so this is how the wave function is influenced. What about the tight binding model, right? Let's consider the effect of A on tight binding model. And all we need to do is just consider like one general hopping term. Typically what we have is like something like that, Tij, Ei dagger, Ej. And what this means is like we have like some side Ri, some other side Rj. So there's like some localized function here, there's some localized function there. And because of the overlap of these functions, there's like some kind of quantum tunneling, which is Tij, and the particle can hop from Ri to Rj. But here we have seen if the particle goes from a place to another place, it needs to pick up like this additional Aharonov-Bohm phase. Then, so this is without the magnetic field. In the presence of magnetic field, what we need to do is Tij should go to Tij times exponential minus I q over h bar c goes from Ri to Rj. So this is the r prime dot a of r prime, and this thing is called Peierls substitution. So basically you can start with like a tight binding model, and when you turn on the magnetic field you have like a vector potential, and all you need to do in the tight binding model is like modify the hopping parameters or hopping amplitudes like this with an overall phase, and solve the tight binding model with these parameters, which we are going to see an example. Okay, let's take a 5-minute break. Continue in the second hour.